tonight, I want to tell you about something that's been quietly bothering physicists for decades. It's not a particle, it's not a force, and it's not really a single discovery. It's more like a feeling, a nagging, uncomfortable suspicion that the universe we live in is far, far too perfect. Not perfect in the way you might mean when you describe a sunset or a piece of music. Perfect in the way that a combination lock is perfect, every number dialed to exactly the right position, and if any one of them had been even slightly different, the lock would never have opened. The door to existence, to stars, to atoms, to you lying here right now listening to this. That door appears to be held open by an almost impossibly precise set of numbers, and nobody knows why. Let me start with something simple. You probably know that the universe runs on certain rules. Gravity pulls things together. Light travels at a certain speed. Atoms hold together because of forces between their parts. These aren't vague tendencies. They're governed by specific numbers, specific values, that physicists call the fundamental constants of nature. And here's the thing. Those numbers didn't have to be what they are. There's no equation we know of that says the speed of light must be 299,792,458 meters per second, or that the gravitational constant must be 6.674 times 10 to the minus 11. These values appear to be baked into the fabric of reality from the very beginning, like settings on some cosmic control panel that were dialed in before the universe even started expanding. And they've remained fixed ever since. Now, that alone is interesting, but what makes it genuinely unsettling is what happens when you start asking a different kind of question. Not what are the values of these constants, but what would happen if they were different? What if the gravitational constant were a little stronger? What if the charge on an electron were slightly larger? What if the strong nuclear force, the one that holds the cores of atoms together, were tuned just a hair differently from what it is? And the answer, over and over and over again, is the same. Everything falls apart. Not metaphorically, literally. If you change almost any of these fundamental numbers by even a tiny fraction, you don't get a slightly different universe. You get no universe at all. No stars, no chemistry, no planets, no life. Nothing that you or I would recognize as a cosmos. This is what physicists call the fine-tuning problem, and it is, I think, one of the deepest and most beautiful mysteries in all of science. Let me give you a sense of the numbers involved, because the abstractions don't do it justice. Start with gravity. Gravity is, by far, the weakest of the four fundamental forces. It's almost laughably weak compared to the others. The electromagnetic force, the one responsible for chemistry, for light, for the fact that your hand doesn't pass through the table, is roughly 10 to the 36th power stronger than gravity. That's a 1, followed by 36 zeros. If gravity and electromagnetism arm wrestled, electromagnetism wouldn't just win. It would win by a factor so large that the number doesn't even fit comfortably in human language. And yet, gravity is absolutely essential. Without gravity, gas clouds in the early universe would never have collapsed into stars. And without stars, there's no fusion, no heavy elements, no carbon, no oxygen, no iron, nothing beyond the hydrogen and helium that came out of the Big Bang. So gravity needs to exist. But here's where the fine-tuning comes in. Gravity also needs to be weak. If gravity were even slightly stronger, and by slightly, I mean by a factor that seems almost negligible at cosmic scales, stars would burn through their fuel catastrophically fast. A star like our Sun, instead of burning steadily for 10 billion years, giving lifetime to evolve on a planet orbiting it, would blaze through its hydrogen in a few million years, maybe less. the universe would be full of brilliant, short-lived stars that exploded long before anything interesting could happen on any planet nearby. On the other hand, if gravity were slightly weaker, gas clouds might never collapse at all. You'd have a universe of thin, cold fog, stretching out forever, with no stars, no galaxies, no light, just darkness. So gravity has to be in a sweet spot, not too strong, not too weak. And the range of that sweet spot, compared to the full range of values gravity could theoretically take, is breathtakingly narrow. It's like spinning a dial that goes from 0 to 1,000,000,000 and needing to land within a hair's width of one particular number. And gravity got it right. Now, you might be thinking, okay, that's one coincidence. Maybe it's just luck. Fair enough. Let's talk about another constant, the strong nuclear force. This is the force that holds protons and neutrons together inside the nucleus of every atom. It's incredibly powerful. That's why it's called the strong force. But it operates over an absurdly short range. It only reaches across distances roughly the width of an atomic nucleus, about a femtometer, which is a millionth of a billionth of a meter. Beyond that distance, it essentially doesn't exist. The strength of the strong force is characterized by a number that physicists call the strong coupling constant. And this number is critical in a way that goes far beyond just keeping nuclei together. It determines what kinds of atoms can exist. See, when the universe was very young, just a few minutes old in fact, the strong force was busy assembling the first atomic nuclei out of the protons and neutrons that had formed moments earlier. This period is called Big Bang nucleosynthesis, and it's one of the most precisely understood events in all of cosmology. During those first few minutes, the strong force fused protons and neutrons into the nuclei of hydrogen, helium, and tiny amounts of lithium. And the exact proportions it produced, about 75% hydrogen, 25% helium, and a trace of lithium, match what we observe in the oldest, most pristine gas clouds in the universe today. It's one of the great triumphs of the Big Bang theory. But here's where the fine-tuning appears. If the strong force were about 2% stronger than it is, something remarkable would happen. Protons could fuse directly with other protons, without needing to first convert one of them into a neutron. That might sound like a minor technical detail, but it would change everything. In our universe, the fact that proton-proton fusion is so difficult is what makes stars burn slowly. It's what gives our sun its 10 billion-year lifetime. If protons could fuse easily, stars would be nuclear bombs. They'd ignite and exhaust their fuel almost instantly. No stable stars. No long-lived solar systems. No time for the slow, patient process of evolution. And if the strong force were about 5% weaker, then it couldn't hold a proton and a neutron together at all. Deuterium, the simplest composite nucleus, just one proton and one neutron, wouldn't be stable. And deuterium is a crucial stepping stone in the chain of nuclear reactions that builds heavier elements. Without deuterium, stars can't fuse hydrogen into helium in the way our sun does. The whole nuclear pathway that powers stars and creates the elements of life would be broken. You'd have a universe of hydrogen and nothing else. No carbon, no oxygen, no iron, just an endless sea of the simplest possible atom drifting in the dark. So the strong force, too, sits in a narrow window. Change it by a few percent in either direction, and the universe becomes either a fireworks show that's over in seconds or a featureless void of hydrogen gas. Let me pause on that for a moment, because I think it's worth sitting with. We're not talking about changing these constants by a factor of 10 or 100. We're talking about a few percent, sometimes less, and the consequences are total. Stars or no stars, chemistry or no chemistry. A universe that can produce life, or a universe that's utterly sterile. That's the kind of knife edge we're sitting on, and we're just getting started. Let's talk about the electromagnetic force. This is the force you're most familiar with in daily life, even if you don't think of it that way. Every time you see light, that's electromagnetism. Every time you touch something and feel resistance, that's the electromagnetic repulsion between the electron clouds of atoms. Chemistry itself, the way atoms bond to form molecules, the way molecules interact to form proteins, the way proteins fold to create the machinery of life, all of this is electromagnetism at work. The strength of the electromagnetic force is captured by a number called the fine structure constant. It's usually written as the Greek letter alpha, and its value is approximately 1/137. That number, 137, fascinated some of the greatest minds of the 20th century. Richard Feynman, who was as brilliant and irreverent a physicist as ever lived, once called it one of the greatest damn mysteries of physics. He said that all good theoretical physicists put this number up on their wall and worry about it. Wolfgang Pauli, another giant of quantum mechanics, was so obsessed with the number 137 that when he was hospitalized near the end of his life and learned his room number was 137, he reportedly told a colleague that he would never leave that room alive. He didn't. But why does 137 matter so much? Because it determines the strength of electromagnetic interactions at the quantum level. It governs how strongly electrons are bound to nuclei, how easily atoms can absorb and emit light, and how the periodic table of elements is structured. And it turns out, this number is also fine-tuned. If alpha were significantly larger, say 120 instead of 137, electrons would be bound more tightly to their nuclei. Carbon, the element that forms the backbone of every known form of life, would be less able to form the complex chains and rings of chemical bonds that make organic chemistry possible. Water might behave differently. The chemistry of life as we know it would become impossible or radically different. If alpha were much smaller, say 1/170, atoms would hold their electrons more loosely, stars would burn differently, the energy levels of atoms would shift, and the specific nuclear reactions inside stars that produce carbon and oxygen might not work the way they do. The periodic table would look different. The exquisite specificity of biochemistry, the fact that certain molecules fit together like lock and key, the fact that DNA can store information and replicate itself, depends on the electromagnetic force being exactly as strong as it is. And here's a connection that might surprise you. The fine structure constant doesn't just affect chemistry. It also determines how light interacts with matter, which affects how heat moves through the interiors of stars, which affects how stars evolve, which affects whether they explode as supernovae and scatter heavy elements into space, which affects whether those elements can come together to form rocky planets like Earth. Pull on this one thread, and the entire tapestry of astrophysics unravels. Now, I've been telling you about these constants one at a time, and each one individually seems improbably well-tuned. But the real puzzle is deeper than any single constant. It's the fact that they all seem to be tuned simultaneously. It's not just that gravity is the right strength. It's that gravity is the right strength, and the strong force is the right strength, and the electromagnetic force is the right strength, and the weak force is the right strength, and the masses of the elementary particles are the right masses, and the cosmological constant is the right value, all at the same time. The odds of all of these independent numbers landing in their life-permitting ranges simultaneously is something that makes physicists genuinely uncomfortable. Because the number you get when you try to calculate those odds is not just small. It's absurdly, cosmically, incomprehensibly small, And that brings us to one of the most dramatic characters in this story, a number so seemingly impossible that when physicists first calculated it, many of them refused to believe the result. I'm talking about the cosmological constant. And to tell you about the cosmological constant, I need to tell you about Albert Einstein and about what he called the biggest blunder of his career. It's 1917. Einstein has just published his general theory of relativity, arguably the most beautiful and revolutionary theory in the history of physics. It describes gravity not as a force pulling objects together, but as the curvature of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells objects how to move. It's an idea so elegant that even now, more than a century later, it still takes your breath away if you really sit with it. The mattress you're lying on right now is slightly curving the space-time around it. Your body is following the gentle curvature created by the Earth's mass. That's what keeps you from floating off into the ceiling, not a force reaching up and pulling you down, but the shape of the universe itself, guiding you along a curved path. But Einstein had a problem. When he applied his equations to the universe as a whole, they predicted something he didn't expect and didn't want. The universe couldn't be static. His equations said the universe must be either expanding or contracting. It couldn't just sit there, and in 1917, everyone, Einstein included, believed the universe was eternal and unchanging. A static cosmos was practically a philosophical axiom. So Einstein did something unusual for a man of his genius. He fudged his own equations. He added a term, a small constant, that acted like a kind of anti-gravity, pushing things apart just enough to balance gravity's pull and keep the universe perfectly still. He called this term the cosmological constant, and he gave it the Greek letter lambda. For about a decade, lambda sat quietly in Einstein's equations, doing its job of keeping the universe static. And then, in 1929, an astronomer named Edwin Hubble made one of the most important observations in the history of science. Using the 100-inch Hooker telescope on Mount Wilson in California, Hubble showed that distant galaxies were moving away from us, and that the farther away a galaxy was, the faster it was receding. The universe wasn't static at all. It was expanding, had been expanding for billions of years. Einstein was reportedly devastated. He stripped the cosmological constant from his equations and, according to physicist George Gamow, called it the biggest blunder of his life. Lambda was unnecessary. The universe was expanding on its own, and there was no need for a fudge factor to hold it still. And for the next 70 years, most physicists agreed. The cosmological constant was set to zero and forgotten about. It was a historical curiosity, a rare mistake by the greatest theoretical mind of the 20th century. But then, in 1998, something extraordinary happened. Two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were studying distant Type 1a supernovae. These are a particular kind of exploding star that always reaches roughly the same peak brightness, which makes them useful as cosmic distance markers. By measuring how bright a Type 1a supernova appears from Earth, and comparing that to how bright it actually is, you can figure out how far away it is. And by measuring the redshift of the light, how much its wavelength has been stretched by the expansion of the universe, you can figure out how fast the universe was expanding when that light was emitted. Both teams expected to find that the expansion of the universe was slowing down. That would make sense. Gravity should be pulling everything back together, gradually decelerating the expansion, like a ball thrown upward eventually slows and falls back. But that's not what they found. What they found was the opposite. The expansion of the universe is speeding up. The universe isn't just expanding, it's accelerating. Something is pushing it apart faster and faster, and that something acts exactly like Einstein's cosmological constant. Einstein's biggest blunder turned out to be right. Not in the way he intended. The universe isn't static, but in a deeper way. There really is something acting like a cosmological constant, a kind of energy woven into the fabric of empty space itself, pushing the universe apart. Physicists call it dark energy, and it accounts for about 68% of the total energy content of the universe. You, me, the stars, the galaxies, all the ordinary matter and energy we can see and touch, make up less than 5%. The rest is dark matter and dark energy is by far the dominant component. And here's where the fine-tuning gets truly staggering. When physicists try to calculate what the cosmological constant should be, using quantum field theory, our best description of how particles and forces work at the smallest scales, they get an answer that is roughly 10 to the 120th power larger than the value we actually observe. Let me make sure you appreciate how big that discrepancy is. 10 to the 120th power. That's a 1 followed by 120 zeros. It is, by some measures, the worst prediction in the entire history of science. The predicted value and the observed value disagree by a factor so enormous that it dwarfs any other mismatch between theory and experiment ever encountered in physics. Now, why does the actual value of the cosmological constant matter so much? Because if it were significantly larger, if it were even a tiny, tiny fraction of what quantum field theory naively predicts, the universe would have blown apart before galaxies could form. Trust your dreams for the future. Imagine the universe in its infancy, just a few 100 million years old, with the first gas clouds beginning to clump together under gravity's gentle pull. Now imagine a cosmological constant, 100 times stronger than what we have. Those gas clouds wouldn't just struggle to clump, they'd be ripped apart. The expansion of space would overpower gravity's ability to form structures. No galaxies, no stars, no planets. Just an ever-thinning mist of particles racing away from each other into infinite emptiness. And if the cosmological constant were negative, if it acted as an attractive force rather than a repulsive one, the universe would have recollapsed long ago. It would have expanded, slowed, stopped, and then fallen back in on itself in a kind of reverse Big Bang, a big crunch. Everything crushed back into a point before anything interesting could happen. So the cosmological constant needs to be positive, but incredibly, absurdly small. It needs to be small enough that it doesn't interfere with the formation of galaxies and stars, but large enough that it eventually becomes noticeable at cosmic scales. And the value it actually has, the value discovered in 1998, threads that needle with almost unbelievable precision. It is not 0, but it is 120 orders of magnitude smaller than what our best theories predict. It's as if you had a volume knob that went from 0 to a number with 120 digits, and someone set it to one of the lowest possible notches, just barely above 0, and that incredibly specific, seemingly arbitrary setting turned out to be exactly what was needed for the universe to produce galaxies, stars, planets, and eventually you. Nobel laureate Steven Weinberg, who thought deeply about this problem for decades, once pointed out that the cosmological constant is the one quantity in physics where the fine-tuning is so extreme that it constitutes an argument, not proof, but an argument for something very strange going on. And that strangeness, that sense that the numbers are too good to be accidental, is at the heart of everything I want to tell you tonight. But let me pull back from the cosmological constant for a moment, because there's another fine-tuning story that I love, and it involves one of the most cantankerous, brilliant, and wonderfully stubborn physicists of the 20th century, Sir Fred Hoyle. Hoyle was a British astronomer and cosmologist who made enormous contributions to our understanding of how the elements are formed inside stars, a process called stellar nucleosynthesis. He was also famously contrarian. He coined the term Big Bang as a dismissive joke. He didn't believe in it, preferring his own steady-state theory of the universe, in which the cosmos had no beginning and would have no end. History proved him wrong about that. But on the question of how stars forge the elements, he was spectacularly right, and his greatest prediction remains one of the most astonishing examples of fine-tuning in all of physics. The story goes like this. In the early 1950s, Hoyle was working on the problem of how carbon is made inside stars. This is a crucial question, because carbon is the fourth most abundant element in the universe and the foundation of all known life. Every carbon atom in your body was forged in the nuclear furnace of a star that lived and died billions of years ago. You are, quite literally, stardust. But how do stars make carbon? The basic process seems straightforward. You take 3 helium nuclei, 3 alpha particles, each consisting of 2 protons and 2 neutrons, and you fuse them together to make a carbon-12 nucleus. The problem is that this triple alpha process, as it's called, is incredibly unlikely under normal circumstances. Smashing 3 helium nuclei together simultaneously is a bit like expecting 3 billiard balls to collide at exactly the same point, at exactly the same time. It almost never happens. And yet, the universe is full of carbon. Stars produce enormous quantities of it. So Hoyle reasoned that there must be something making the triple alpha process much more efficient than it appeared. He predicted that there must be an excited energy state of the carbon-12 nucleus, a resonance, at a very specific energy, right around 7.65 million electron volts above the ground state. This resonance would act like a trap, making it far easier for 3 helium nuclei to stick together and form stable carbon. Without it, the triple alpha process would be so rare that the universe would contain virtually no carbon. This was a stunning prediction. Hoyle was essentially saying, I know this energy level must exist, because if it doesn't, we wouldn't be here. He then contacted Willie Fowler, an experimental nuclear physicist at Caltech, and asked him to look for it. Fowler was skeptical. Hoyle was, after all, an astronomer telling a nuclear physicist what to find in his own laboratory. But Fowler's team ran the experiment, and they found the resonance almost exactly where Hoyle had predicted it would be. The energy level was at 7.6549 million electron volts. Hoyle was right. Hoyle was right. And here's the fine-tuning. That resonance, the Hoyle state as it's now called, exists at an energy that is suspiciously, almost eerily, well matched to the conditions inside red giant stars. If the energy of the Hoyle state were just 0.5% higher or lower than its actual value, the resonance wouldn't work properly. Carbon production in stars would be negligible. The universe would be carbon poor. And since carbon is essential for the kind of complex chemistry that leads to life, a universe without abundant carbon would almost certainly be a universe without life. But the fine-tuning goes deeper. Even after carbon is made, it needs to survive. The next step in stellar nucleosynthesis is for carbon to fuse with another helium nucleus to make oxygen-16, and it turns out that there is not a resonance at just the right energy to make this reaction extremely efficient. If oxygen-16 had a resonance state near the relevant energy, then virtually all the carbon produced in stars would quickly be converted to oxygen, and you'd have a universe rich in oxygen, but poor in carbon. Once again, complex chemistry and life would be in trouble. So you need a resonance in carbon to make it efficiently, and you need the absence of a resonance in oxygen to keep it from being destroyed. Both of these conditions are met in our universe, and both depend on the precise values of the strong force and the electromagnetic force. Change the strong coupling constant by a fraction of a percent, and one or both of these conditions fail. Hoyle himself was deeply shaken by this realization. He later wrote that his atheism was greatly shaken by the discovery, and he began to suspect that a super-intellect had monkeyed with physics as well as chemistry and biology. Now, whether or not you agree with Hoyle's interpretation, the physics itself is beyond dispute. The nuclear energy levels that make carbon production possible and that prevent its immediate destruction are finely tuned to a degree that seems almost designed, almost intentional, almost suspicious. And this is the pattern that keeps repeating, no matter which constant you look at. The mass of the neutron, for instance. The neutron is slightly heavier than the proton, by about 0.14%, or 1.293 million electron volts. That tiny mass difference is critical. Because the neutron is heavier, a free neutron, one not bound inside a nucleus, is unstable. It decays into a proton, an electron, and an antineutrino with a half-life of about 10 minutes. This instability is essential for the chemistry of the universe. If the neutron were lighter than the proton, if the mass difference were reversed, then protons would be the unstable ones. They'd decay into neutrons, and you'd lose all the hydrogen in the universe. No hydrogen means no water, no organic chemistry, no stars powered by hydrogen fusion. The universe would be a very different and almost certainly lifeless place. But it gets even more delicate. If the neutron were heavier than it is by just a little bit more, say, by an extra 0.1%, neutrons would decay so quickly that very few would survive the first few minutes of the Big Bang to be captured into helium nuclei. The universe would be almost entirely hydrogen. If the neutron were lighter by a similar amount, but still heavier than the proton, neutrons would be more stable, and the Big Bang would produce much more helium and less hydrogen. The balance of elements, the raw materials for stars and planets and people, depends on this tiny mass difference being right where it is. Think about that. The entire chemical composition of the universe, the balance between hydrogen and helium that determines what kinds of stars can form, how long they can burn, what elements they can forge, depends on a mass difference that's less than 0.2% of the neutron's total mass. If someone adjusted that fraction by a hair, the universe would be uninhabitable. Now, let me introduce you to another constant that doesn't get as much attention as gravity or the strong force, but that might be the most finely tuned of all: the ratio of electromagnetic force strength to gravitational force strength. This ratio is roughly 10 to the 36th power. Electromagnetism is 10 to the 36th times stronger than gravity, and that enormous gap is not a bug, it's a feature. Here's why. Stars exist because of a balance between two forces: gravity, which tries to crush them, and the pressure from nuclear fusion and radiation, which pushes outward and holds them up. If gravity were much stronger relative to electromagnetism, stars would be smaller, denser, and would burn through their fuel much faster. The entire stellar life cycle would be compressed. Planets might not have time to form before their star expires. On the other hand, if gravity were much weaker, stars might not ignite at all, because the gravitational compression at their cores wouldn't be sufficient to trigger nuclear fusion. The physicist Brandon Carter showed in the 1970s that the existence of stars with properties suitable for life, stars that burn stably for billions of years, that produce the right elements, that emit energy at wavelengths useful for photosynthesis, requires this ratio of forces to be within a surprisingly narrow band. The universe didn't just luck into having stars. It lucked into having exactly the right kind of stars. And there's something else I want to tell you about, because it's one of those details that, once you learn it, you can never quite forget. It involves the most recently discovered fundamental parameter of our universe, the Higgs field, and the way it quietly determines the mass of everything you've ever touched, seen, or been. The Higgs field was predicted theoretically in 1964 by Peter Higgs, and, independently, by François Englert and Robert Brout, along with several other physicists. The basic idea is that empty space isn't really empty. It's filled with a quantum field, the Higgs field, that has a non-zero value everywhere in the universe. It's as if the entire cosmos is soaked in an invisible substance, and when certain particles move through this substance, they interact with it and acquire mass. The more strongly a particle interacts with the Higgs field, the more massive it is. Electrons interact weakly, so they're light. Top quarks interact strongly, so they're heavy, about 340,000 times heavier than an electron. For nearly 50 years, the Higgs field was a theoretical prediction without direct experimental confirmation. Then, on July 4, 2012, two massive experimental collaborations at the Large Hadron Collider at CERN, the ATLAS and CMS experiments, announced the discovery of the Higgs boson, the particle associated with the Higgs field. It was one of the great moments in the history of science. Peter Higgs, then 83 years old, was in the audience. He reportedly wiped tears from his eyes. Now, the Higgs field's vacuum expectation value, the strength of the field that permeates all of space, is about 246 billion electron volts, and that particular value turns out to be absolutely critical, because it's the Higgs field that gives the quarks inside protons and neutrons their masses, and it's those quark masses that determine the mass difference between the neutron and the proton, the same mass difference we talked about earlier, the one that has to be precisely right for hydrogen to be stable and for the Big Bang to produce the right mix of elements. Here's the fine-tuning. If the Higgs vacuum expectation value were significantly larger, quarks would be heavier, the neutron-proton mass difference might change in ways that destabilize hydrogen or helium, and the nuclear physics of stars would be completely altered. If the Higgs value were significantly smaller, quarks would be lighter, nuclear binding energies would shift, and once again the careful balance that allows carbon and oxygen to be produced in stars would be disrupted. But the fine-tuning of the Higgs goes deeper than its effect on quark masses. There's a puzzle that theoretical physicists call the hierarchy problem, and it's one of the most vexing issues in all of fundamental physics. The problem is this: the Higgs field is sensitive to quantum corrections from all the heavier particles in the theory. When you calculate the expected energy of the Higgs field using quantum field theory, the contributions from virtual particles at very high energies tend to push the Higgs mass up to the highest energy scale in the theory, typically the Planck scale, which is roughly 10 to the 19th billion electron volts. That's about 10 to the 17th times larger than the observed value. So the Higgs mass, like the cosmological constant, appears to be unnaturally small. It's as if two enormous numbers, the bare Higgs mass and the quantum corrections to it, nearly perfectly cancel each other out, leaving behind a tiny residual that gives us the Higgs field we observe. This cancellation has to work to about 1 part in 10 to the 34th. If it were off by even a tiny fraction, the Higgs value would be radically different, and the masses of all the fundamental particles, electrons, quarks, W and Z bosons, would change accordingly. The entire character of matter would be transformed. Physicists spent decades trying to solve the hierarchy problem. The most popular proposed solution was supersymmetry, a theoretical framework that posits a symmetry between the two main types of particles in nature, bosons and fermions. In a supersymmetric theory, every known particle has a superpartner, an electron has a selectron, a quark has a squark, and so on. These superpartners would contribute quantum corrections to the Higgs mass that precisely cancel the troublesome contributions from the known particles, neatly solving the hierarchy problem. It was an elegant idea, and for decades, it was the leading candidate for physics beyond the Standard Model. Thousands of papers were written about it. Careers were built on it. The Large Hadron Collider at CERN was built, in part, to find superpartner particles. But when the LHC turned on and began smashing protons together at unprecedented energies, it found nothing. No selectrons, no squarks, no gluinos. The simplest and most elegant versions of supersymmetry predicted particles that should have been visible at the LHC's energies, and they weren't there. This non-discovery was, in its own way, as important as the discovery of the Higgs boson. It didn't definitively rule out supersymmetry. The superpartners could be heavier than the LHC can reach, but it eliminated the versions of the theory that would have naturally solved the hierarchy problem. And that left the fine-tuning of the Higgs mass unexplained. As of right now, we don't know why the Higgs field has the value it has, or why that value isn't driven up to the Planck scale by quantum corrections. It's just another instance of the constants of nature, sitting at a value that seems, from the perspective of our best theories, improbable. Let me tell you about yet another facet of this puzzle, because the more you look, the more fine-tuning you find. Consider the ratio of matter to antimatter in the early universe. According to our understanding of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. And when matter meets antimatter, they annihilate each other, producing pure radiation. If the Big Bang had produced exactly equal amounts, all the matter and antimatter would have annihilated, leaving behind a universe of nothing but photons. No atoms, no stars, no planets, no you. But that didn't happen. For every billion antimatter particles produced in the Big Bang, there were 1,000,000,001 matter particles. That tiny asymmetry, one extra matter particle for every billion, is the reason anything material exists at all. After the Great Annihilation, that 1 in a billion surplus was all that was left, and it became everything. Every galaxy, every star, every atom in your body. You are the residue of a cosmic near cancellation, the slight remainder of a nearly perfect symmetry. And the origin of that asymmetry is still not fully understood. We know it happened. The evidence is literally everywhere you look. But the precise mechanism that produced one extra matter particle per billion is one of the great unsolved problems in physics. It goes by the name baryogenesis, and various theories have been proposed, but none has been definitively confirmed. Whatever the mechanism was, it had to produce exactly the right amount of excess matter. Too much, and the early universe would have been too dense, collapsing into black holes before stars could form. Too little, and there wouldn't be enough matter to build interesting structures. Once again, the actual value sits in a narrow window. And while we're on the subject of the early universe, let me tell you about something called the flatness problem, which is really another manifestation of fine-tuning, dressed in different clothes. The geometry of the universe, whether it's curved like a sphere, curved like a saddle, or flat like a table, depends on a parameter called the density parameter, usually written as omega. If omega is greater than 1, The universe is positively curved and finite. If omega is less than 1, it's negatively curved and infinite. If omega is exactly 1, it's flat. Observations show that omega is very, very close to 1. The universe is flat to a remarkable degree of precision. And here's the thing. In a universe governed by the original Big Bang theory, without inflation, flatness is unstable. If omega started out even slightly different from 1 in the very early universe, say 1.000001 or 0.999999, it would rapidly diverge from 1 as the universe expanded. By now, billions of years later, it would be either enormously greater than 1 or enormously less than 1. The fact that it's still so close to 1 today means that in the first fraction of a second after the Big Bang, omega had to be equal to 1 to something like 59 decimal places. 1 part in 10 to the 59th. Now, inflation solves this problem by driving omega toward 1, regardless of its initial value. That's one of inflation's great successes. But the flatness problem still highlights the general theme. The universe's large-scale properties depend on initial conditions that were set to extraordinary precision. Whether that precision is explained by inflation, by the multiverse, by a deeper theory, or by something else entirely, the fact remains that the universe started in an extraordinarily special state. Let me tell you about one more person in this story, because his contribution captures something essential about the spirit of the fine-tuning inquiry. His name is Martin Rees, and he's the Astronomer Royal of Britain and one of the most distinguished cosmologists alive. In 1999, Rees wrote a book called Just 6 Numbers, in which he identified 6 fundamental constants that he argued are the most critical for the existence of the universe as we know it. The 6 numbers are the ratio of electromagnetic to gravitational force strength, the strength of the strong forces binding of nucleons in nuclei, the density of the universe relative to the critical density, the cosmological constant, the amplitude of the density fluctuations in the early universe that seeded the formation of galaxies, and the number of spatial dimensions. Rees argued that each of these 6 numbers is set to a value in a narrow range, and that if any of them were significantly different, the universe would lack the complexity needed for life. His book was remarkable for the clarity with which it presented the fine-tuning argument to a general audience, and for Rees's own measured, thoughtful approach to the implications. He didn't claim to have the answer. He simply laid out the evidence and invited the reader to grapple with the mystery. One of the numbers Rees highlighted, the one I haven't talked about yet tonight, is the amplitude of the primordial density fluctuations. This is the parameter that characterizes how lumpy the early universe was. Right after the Big Bang, the universe was extraordinarily smooth, almost perfectly uniform in density. But it wasn't perfectly uniform. There were tiny variations, fluctuations in density of about 1 part in 100,000. These fluctuations were the seeds of all future structure. Regions that were slightly denser than average had slightly more gravity, which attracted slightly more matter, which increased their density further, which attracted more matter still. Over billions of years, this process amplified those tiny initial fluctuations into the galaxies, galaxy clusters, and cosmic web we see today. And the amplitude of those fluctuations, about 1 part in 100,000, is itself finely tuned. If the fluctuations had been much larger, say 1 part in 1,000, the overdense regions would have collapsed too quickly, forming mostly black holes and dense clumps, rather than galaxies, with the kind of gentle structure needed for stars and planets. If the fluctuations had been much smaller, say 1 part in 10 million, gravity would never have amplified them enough to form galaxies at all. The universe would have remained a thin, featureless gas, expanding and cooling forever, without forming any structures. So even the lumpiness of the early universe, the statistical character of the primordial fluctuations, had to be just right. Not the specific pattern of fluctuations. That part appears to be random, consistent with quantum mechanics, but their overall amplitude, how big the lumps were, on average. And that amplitude, like everything else we've discussed tonight, sits in a narrow, life-permitting range. I find it astonishing when you put it all together. The strength of gravity, the strength of the strong force, the electromagnetic coupling constant, the cosmological constant, the Higgs vacuum expectation value, the quark masses, the neutron-proton mass difference, the matter-antimatter asymmetry, the flatness of the universe, the amplitude of primordial fluctuations, the number of spatial dimensions, the energy level of the Hoyle state in carbon-12. Every single one of these parameters is set to a value in a narrow range, and every single one of them needs to be where it is for the universe to produce anything more interesting than a structureless soup of particles. And here's what I keep coming back to. These parameters appear to be independent of each other. There's no known law that connects the strength of gravity to the mass of the electron. There's no equation that relates the cosmological constant to the amplitude of primordial fluctuations. These are, as far as we can tell, separate dials on the cosmic control panel, each of which had to be set independently to its life-permitting value. The probability of all of them landing in their respective sweet spots simultaneously, by chance, is, well, it's a number that makes your head swim if you try to think about it too hard. And that's the fine-tuning problem, in all its glory. It's not one coincidence. It's dozens of coincidences, all at once, with no apparent connection between them, all pointing in the same direction, toward a universe that can produce complexity, chemistry, and consciousness. And as of right now, at this moment in the history of human knowledge, we have no definitive explanation for why. So let's take a breath here, because I've been throwing a lot of numbers and forces at you, and I want to step back and look at the bigger picture. We've talked about gravity, the strong force, the electromagnetic force, the cosmological constant, the neutron-proton mass difference, the Hoyle state in carbon, the ratio of force strengths. And in every single case, we find the same thing. The value of the constant sits in a narrow range, and if it were outside that range, often by just a few percent, sometimes by far less, the universe would be sterile. No complexity, no chemistry, no life. Now, here's the question that all of this raises, and it's the question that has kept physicists, philosophers, and theologians arguing for the better part of a century. Why? Why are these numbers what they are? Why do they fall in the tiny life-permitting range? Is it a coincidence? Is it evidence of design? Is there some deeper law we haven't found yet that requires these numbers to have exactly these values? Or is something else going on? Something even stranger? Let me walk you through the main answers that have been proposed, because each one is fascinating in its own right, and none of them is entirely satisfying. The first answer is the simplest. It's just a coincidence. The constants are what they are, because that's what they are. There's no deeper reason. We observe a life-permitting universe because, well, if the universe weren't life-permitting, we wouldn't be here to observe it. This is sometimes called the weak anthropic principle, and it was articulated most clearly by the physicist Brandon Carter at a symposium in Krakow in 1973, on the occasion of the 500th anniversary of Copernicus's birth. Carter pointed out that our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. In other words, We shouldn't be surprised that the universe appears fine-tuned for life, because a universe that wasn't fine-tuned for life would contain no one to be surprised. And that's true, as far as it goes. It's logically airtight, but many physicists find it unsatisfying, because it doesn't actually explain anything. It's a bit like being dealt a royal flush in poker and saying, well, some hand had to come up. True, but that doesn't explain why this particular hand. If you were dealt a royal flush 10 times in a row, you'd start suspecting the deck was stacked, no matter how logically possible it was for those hands to arise by chance. The fine-tuning of the constants feels like being dealt a royal flush in a game with 1 trillion cards in the deck. Yes, it's possible, but the odds are so staggeringly against it that most physicists feel compelled to look for a deeper explanation. The second answer is design. The idea that the constants were chosen, deliberately, by some kind of intelligence. This is the argument from fine-tuning for the existence of God, or at least for some kind of cosmic designer. It's been made by physicists and philosophers alike, and in various forms it predates the modern fine-tuning discussion by centuries. The idea is simple. The constants look designed because they are designed. Some mind, some intelligence, some creative force set the dials of the universe to the values needed for complexity and life. I want to be respectful of this view, because many thoughtful people hold it, but I also want to be honest about its scientific status. As an explanation within physics, it doesn't really explain anything. It just pushes the question back a step. Who or what designed the designer? What determined the properties of the intelligence that chose the constants? And why these particular values, rather than others, that might also permit life? The design hypothesis is not testable or falsifiable in any standard scientific sense, which doesn't necessarily mean it's wrong, but it does mean it falls outside the scope of what physics can address. It's a metaphysical answer to a physical question, and many scientists, not all, but many, prefer to keep looking for a physical answer. The third answer is the one that has generated the most excitement and the most controversy in contemporary physics. It's the idea that our universe is just one of an unimaginably vast number of universes, a multiverse, and that each universe in this collection has different values for the fundamental constants. In some universes, gravity is too strong and everything collapses. In some, the strong force is too weak and atoms fall apart. In some, the cosmological constant is too large and space expands too fast for anything to form. But in a tiny fraction of these universes, an incomprehensibly tiny fraction, the constants fall in the life-permitting range. And we, of course, find ourselves in one of those rare, lucky ones, because we couldn't exist anywhere else. This is a deeply strange idea, and when I first encountered it, my reaction was probably similar to yours right now. It sounds like science fiction. It sounds like physicists just made up an infinite number of invisible universes to avoid having to explain our own. And honestly, that criticism has some force. But the multiverse idea didn't come out of nowhere. It emerged naturally, some would say inevitably, from our best theories of fundamental physics. Let me explain how. The story starts with inflation. In the early 1980s, a young physicist named Alan Guth was working at the Stanford Linear Accelerator Center, struggling with some deep problems in cosmology. The Big Bang theory was enormously successful, but it had a few stubborn puzzles. Why is the universe so flat, so close to the boundary between expanding forever and eventually recollapsing? Why is the cosmic microwave background radiation, the afterglow of the Big Bang, so uniform in temperature across the sky, even in regions that could never have been in contact with each other? Why do we not see certain exotic particles, magnetic monopoles, that grand unified theories predicted should be everywhere? Guth proposed a radical solution. He suggested that in the first unimaginably tiny fraction of a second after the Big Bang, during a period lasting perhaps 10 to the minus 36 seconds, the universe underwent a phase of incredibly rapid expansion. Not the gentle, steady expansion we see today, but an exponential blow-up, with the universe doubling in size every 10 to the minus 37 seconds or so. In the span of maybe 10 to the minus 32 seconds, a region smaller than a proton expanded to something larger than the observable universe. This idea, cosmic inflation, solved all three puzzles at a stroke. The universe is flat because inflation stretched it flat, like the surface of an expanding balloon. The temperature is uniform because the entire observable universe was once a tiny region that had time to reach thermal equilibrium before inflation blew it up. And monopoles are absent because inflation diluted them into undetectability. Inflation was a triumph, and subsequent observations, particularly of the detailed patterns in the cosmic microwave background, have confirmed its predictions with stunning precision. But inflation, it turns out, has a consequence that Guth and others didn't fully anticipate. In many versions of inflationary theory, inflation doesn't stop everywhere at once. It stops in some regions, creating pocket universes, like bubbles forming in a pot of boiling water, but continues in the space between them. And in that continuing inflationary space, new pocket universes are constantly forming. Each pocket universe undergoes its own Big Bang, its own cooling, its own formation of particles and forces. And here's the key. In many theoretical frameworks, the values of the fundamental constants can differ from one pocket universe to another. This is called eternal inflation, and it produces a multiverse, a vast, possibly infinite collection of pocket universes, each with potentially different physics. Our universe is just one bubble in an endless, eternally inflating foam. Now, eternal inflation is not the only road to the multiverse. String theory, the leading candidate for a theory of everything, which proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings of energy, also leads to a multiverse. String theory has a feature that initially seemed like a bug. It doesn't predict a unique set of physical laws. Instead, it predicts an enormous number of possible configurations, an enormous number of possible sets of constants, particles, and forces. The number of these possible configurations is estimated to be something like 10 to the 500th power. That's a number so large that you could write it out as a 1 followed by 500 zeros. Each configuration corresponds to a different possible universe with different physical laws. This collection of possible universes is called the string theory landscape, and it was described most influentially by the physicist Leonard Susskind, who, along with others, argued that eternal inflation could populate this landscape, could actually create real, physical universes corresponding to each of these configurations. In this picture, the reason our constants have the values they do is not because those values are special or necessary, but because every possible set of values is realized somewhere, and we happen to be in a corner of the landscape where the constants permit life. If you're feeling a bit dizzy at this point, you're not alone. The multiverse is one of the most contested ideas in modern physics. Some physicists, Susskind, Max Tegmark, Sean Carroll, find it compelling, even beautiful. Others, Paul Steinhardt, Roger Penrose, Sabine Hossenfelder, argue that it's unfalsifiable and therefore not science. If you can't observe the other universes, If you can't test whether they exist, then what's the point of positing them? How is the multiverse different from saying, a wizard did it? This is a legitimate worry, and it touches on deep questions about what science is and what counts as a scientific explanation. But the multiverse's defenders push back. They argue that the other universes aren't a separate hypothesis. They're a prediction of theories, inflation and string theory, that were developed for entirely independent reasons, and that make testable predictions in their own right. You don't reject the existence of distant galaxies just because you can't visit them. And the multiverse, they say, is similar. It's a consequence of well-motivated physics, not a separate postulate. Let me tell you about a beautiful thought experiment that might help clarify why the multiverse appeals to some physicists, even those who are uncomfortable with its implications. Imagine you're a fish in a pond. You've never been outside the pond. You notice that the water temperature, the salinity, the oxygen levels, everything about your pond is just right for fish like you. You might wonder, why is my pond so perfectly suited for me? Is there a pond designer who set everything up? Did the pond have to be this way? But now imagine someone tells you that there are billions of ponds on Earth. Most of them are too hot, too cold, too salty, or too acidic for fish. But in the tiny fraction of ponds that happen to have the right conditions, fish evolved. You're not in a special pond. You're in one of the rare ponds where fish can exist. And of course, that's where you find yourself. Because you couldn't exist anywhere else. That's essentially the multiverse argument. Our universe isn't special. It's just one of the ponds where the conditions happen to be right. And the reason we're here is simply that here is one of the only places we could be. Now, is this satisfying? That's a matter of taste, I think. Some people find it elegant, a clean, simple explanation that doesn't require any special pleading or metaphysical assumptions. Others find it extravagant, trading one mystery, why are the constants fine-tuned? For another, why is there a multiverse? And still others find it defeatist, a retreat from the search for deeper understanding, a shrug dressed up as an answer. But let me tell you about a fourth possibility, one that doesn't get as much attention, but that I find genuinely fascinating. What if the constants aren't actually free parameters? What if there's a deeper theory, a theory we haven't discovered yet, that determines the values of all the fundamental constants from a single, more fundamental principle? In this view, the constants look fine-tuned because they're connected to each other in ways we don't yet understand. They're not independently set on some cosmic control panel. They're consequences of a deeper mathematical structure, and when we find that structure, the fine-tuning mystery will dissolve. This is the dream of a theory of everything, a single mathematical framework that encompasses all the forces, all the particles, all the constants, and shows that they couldn't have been otherwise. Einstein spent the last 30 years of his life searching for such a theory and never found it. String theory was supposed to be it, but as we've seen, it predicts too many possible universes rather than uniquely determining our own. Loop quantum gravity, another approach, is still too incomplete to address the question. Dozens of other proposals, supersymmetry, twistor theory, various approaches to quantum gravity, have been explored, and none has yet achieved the goal of deriving the fundamental constants from first principles. And yet, the history of physics gives us reason for hope. There was a time when the boiling point of water, the specific heat of iron, and the index of refraction of glass all seemed like arbitrary, contingent numbers, constants that simply had to be measured and couldn't be explained. But with the development of statistical mechanics and quantum theory, these quantities were derived from deeper principles. What seemed like arbitrary constants turned out to be consequences of the quantum behavior of atoms and molecules. Maybe the fundamental constants of nature will follow the same pattern. Maybe they seem arbitrary now, only because we don't yet have the deeper theory that explains them. This is speculative, of course. It's a hope, not a result. But it's a hope grounded in the trajectory of physics itself, and many physicists find it more compelling than the alternatives. The physicist Paul Dirac, one of the founders of quantum mechanics, and one of the most mathematically gifted people who ever lived, spent much of his later career thinking about why the constants have the values they do. He proposed that large dimensionless numbers in physics, like the ratio of electromagnetic to gravitational force strength, might be related to each other and might change over time. His large number hypothesis was never confirmed, and his specific proposals didn't pan out. But his instinct that the constants are trying to tell us something, that they're clues to a deeper order, remains influential. Let me circle back now to something I touched on earlier, because I think it's one of the most quietly mind-blowing aspects of the fine-tuning problem. And it has to do with what happens when you don't just fiddle with one constant at a time, but try to change several at once. When physicists first started exploring fine-tuning, they tended to vary one constant while holding all the others fixed. Turn up the gravitational constant, leave everything else alone, see what happens. Turn down the strong force, leave everything else alone, see what happens. And the results, as I've described, were dramatic. Change almost anything by a few percent, and the universe becomes sterile. But then a few physicists, notably Fred Adams, a University of Michigan astrophysicist, and some of his collaborators, started asking a more sophisticated question. What if you change multiple constants simultaneously? Maybe there are compensating adjustments. Maybe if you increase gravity, you can also increase the nuclear force in a way that preserves stellar stability. Maybe the fine-tuning isn't as bad as it looks when you consider the full, multi-dimensional parameter space, rather than just slicing through it one axis at a time. And it turns out, the answer is complicated. In some cases, yes, there are alternative parameter combinations that still produce a universe with some form of complexity. Adams showed that stars could exist, in the sense of gravitationally bound objects powered by nuclear fusion, across a much wider range of parameters than the simple one-at-a-time analysis suggested. The fine-tuning for stars specifically might be less extreme than Hoyle feared. But, and this is important, stars can exist is not the same as a universe can produce life. Even if you can find parameter combinations that allow some kind of star to form, those stars might not produce the right elements, or might not burn for long enough, or might not emit energy in a useful form. The requirements for a life-permitting universe involve many conditions simultaneously: stable atoms, complex chemistry, long-lived energy sources, a range of elements, the right thermodynamics, and when you impose all of those conditions at once, the parameter space shrinks again, dramatically. So the multidimensional analysis softened the fine-tuning problem slightly, but didn't eliminate it. The constants still need to be in a remarkably narrow range, even accounting for compensating adjustments. The universe still looks suspiciously well calibrated. And let me take a moment to talk about something that I think is genuinely profound, and that connects to a deeper question about the relationship between mathematics and physical reality. Because one of the strangest things about the fine-tuning problem isn't just that the constants are what they are, it's that the laws of physics are written in the language of mathematics at all. Eugene Wigner, one of the giants of 20th century physics and a Nobel laureate in 1963, wrote a famous essay in 1960 titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." In it, he marveled at the fact that mathematics, which is, after all, a product of human thought, developed for its own internal beauty and logical elegance, turns out to describe the physical universe with astonishing accuracy. The equations of quantum mechanics, for instance, predict the energy levels of hydrogen to better than 10 decimal places. General relativity predicts the bending of light by gravity with a precision that makes engineering tolerances look sloppy by comparison. Why should this be? Why should the universe obey mathematical laws at all? And why should those laws be ones that human beings, evolved on the African savanna to find food and avoid predators, are capable of discovering? Wigner had no answer. He called the effectiveness of mathematics a gift that we neither understand nor deserve. And his wonder connects directly to the fine-tuning problem, because the fine-tuning of the constants exists within a mathematical framework, the laws of physics, that is itself apparently fine-tuned for intelligibility. The universe isn't just calibrated to produce life. It's calibrated in a way that is mathematically describable, discoverable, and beautiful. This has led some physicists and philosophers to a position that might sound radical, but is actually more common than you'd think. The idea that mathematical structures don't just describe reality, they are reality. Max Tegmark, a cosmologist at MIT, has argued for what he calls the mathematical universe hypothesis, the idea that every consistent mathematical structure exists as a physical reality, and that our universe is just one particular mathematical structure among infinitely many. In this view, the fine-tuning problem becomes a selection effect. We find ourselves in a mathematical structure that permits conscious observers, because that's the only kind of structure in which anyone could be doing the finding. Tegmark's hypothesis is fascinating to think about, even if you ultimately find it too speculative to embrace, because it highlights a deep truth. The fine-tuning problem isn't just a question about the values of some numbers. It's a question about the nature of reality itself. Why does anything exist? Why does it obey laws? Why do those laws have adjustable parameters? And why are those parameters set to values that produce a universe of breathtaking complexity? These are the kinds of questions that blur the boundary between physics and philosophy, and that boundary has always been blurrier than most scientists are comfortable admitting. Einstein himself was deeply philosophical. His approach to physics was guided by aesthetic principles as much as by experimental data. He believed that the laws of nature should be beautiful, simple, and unified. He once said that the most incomprehensible thing about the universe is that it is comprehensible. That sentiment, that wonder at the universe's legibility, is the same impulse that drives the fine-tuning inquiry. Let me loop back now to the everyday, because I've been up in the stratosphere of abstraction, and I want to bring this back to where you are, right now. In this moment, consider the light. If your eyes are still open, there might be some light in the room, the glow of a screen, a nightlight, the faint light seeping under a door. That light is made of photons, which are excitations of the electromagnetic field. Each photon has a specific energy determined by its wavelength, and the relationship between energy and wavelength is governed by Planck's constant, one of the fundamental constants of nature, with a value of about 6.626 times 10 to the minus 34 joule-seconds. That number determines the scale at which quantum effects become important. If Planck's constant were much larger, quantum effects would be visible in everyday life. Objects would visibly tunnel through walls, particles would smear out over large distances, and the classical world of solid objects and definite positions would break down. If Planck's constant were much smaller, atoms would be smaller and tighter. Chemistry would be different, and the quantum mechanical effects that make transistors and lasers possible might not work the way they do. And Planck's constant, combined with the speed of light and the gravitational constant, defines the Planck scale, the fundamental scale of quantum gravity, the regime where our current theories break down entirely. The Planck length is about 1.616 times 10 to the minus 35 meters. The Planck time is about 539.1 times 10 to the minus 44 seconds. The Planck mass is about 2.176 times 10 to the minus 8 kilograms. These numbers define the smallest meaningful distances, the shortest meaningful times, the regime where quantum mechanics and general relativity collide, and neither one, on its own, gives sensible answers. And it's at the Planck scale that the fine-tuning of the cosmological constant becomes most absurd. Because when physicists talk about the cosmological constant being 10 to the 120th smaller than expected, they're comparing it to the natural scale of quantum gravity, the scale where we'd expect the vacuum energy to be set. The cosmological constant is, in Planck units, approximately 10 to the minus 122. That's how small it is. It's essentially zero, from the perspective of fundamental physics. And yet, it's not zero. It has a tiny, positive, non-zero value that dominates the energy budget of the universe and drives its accelerating expansion. Explaining why this number is so close to zero, but not exactly zero, is perhaps the single deepest unsolved problem in theoretical physics. Leonard Susskind has called the cosmological constant problem the worst problem in physics. Raphael Bousseau has called it the greatest crisis in theoretical physics today. And Edward Witten, perhaps the most gifted theoretical physicist since Einstein, once said that he wasn't confident that the cosmological constant problem would be solved in his lifetime, and that it might require an idea as radical as anything in the history of physics. Let me tell you about one more attempt to crack the puzzle, because it illustrates how creative and how desperate the search has become. In the early 2000s, a physicist named Raman Sundram and his collaborator Lisa Randall proposed models with extra dimensions of space, not the tiny, curled-up dimensions of string theory, but large, possibly infinite extra dimensions that are hidden from us because the particles we're made of are confined to a three-dimensional brane, a membrane, embedded in a higher dimensional space. In the Randall-Sundram model, gravity can leak into the extra dimensions, which explains why it's so much weaker than the other forces. It's diluted by the extra space. And the geometry of the extra dimensions can, in some versions of the model, affect the value of the cosmological constant on our brain. These ideas are speculative, and they haven't solved the cosmological constant problem. But they give you a flavor of the kinds of radical thinking that the fine-tuning problem inspires. Physicists are willing to consider extra dimensions, multiple universes, cosmic natural selection, mathematical realism, ideas that, in any other context, might be dismissed as philosophy or science fiction. The fine-tuning problem is so severe, so resistant to conventional explanation, that it has driven some of the most creative minds in physics to the outer edges of speculation. And I think that's actually a good sign. Throughout the history of physics, the deepest advances have come from grappling with the most stubborn puzzles. The ultraviolet catastrophe, the failure of classical physics to predict the spectrum of hot objects, led to quantum mechanics. The incompatibility of Newtonian gravity with the principle of relativity led to general relativity. The bizarre results of the double-slit experiment led to the wave-particle duality and the probabilistic interpretation of quantum mechanics. Each of these puzzles seemed intractable until someone found the key that unlocked it. And when the key was found, it didn't just solve the puzzle, it transformed our entire understanding of reality. Maybe the fine-tuning problem is that kind of puzzle. Maybe it's trying to tell us something fundamental about the nature of reality, something we haven't yet figured out, but that, when we do, will change everything. Maybe the apparently arbitrary values of the constants are clues, breadcrumbs, left by a deeper theory that's waiting to be discovered. And maybe the person who finds that theory is a student somewhere right now, lying in bed, unable to sleep, thinking about why the numbers are what they are. The physicist John Archibald Wheeler, a towering figure in 20th century physics, who coined the terms black hole and wormhole and mentored both Richard Feynman and Kip Thorne, once suggested that the constants of nature might not be truly fundamental at all. He proposed a principle he called it from bit, the idea that the physical world, at its deepest level, is made of information. In Wheeler's vision, every particle, every field, every space-time event derives its existence from answers to yes or no questions, from bits of information. The constants of nature, in this view, might emerge from some underlying informational structure, the way the temperature of a gas emerges from the collective behavior of trillions of molecules. If Wheeler is right, the fine-tuning of the constants might dissolve once we understand the informational substrate from which they arise. Wheeler died in 2008, at the age of 96, without seeing his vision realized, but his ideas continue to influence the cutting edge of physics, particularly in the study of black holes, quantum information, and the holographic principle. The idea, proposed by Gerard Hooft and Leonard Susskind, that the information content of a volume of space can be encoded on its boundary. These ideas are still being developed, and it's too early to say whether they'll shed light on the fine-tuning problem. But they represent the kind of radical rethinking that the problem demands. You know, there's something I find particularly moving about the human side of all this. When you read the accounts of physicists who have spent their lives working on the fine-tuning problem, people like Weinberg, Susskind, Penrose, Rees, you notice something they all share, regardless of which side of the debate they fall on. They all express a kind of reverence for the problem itself, not just intellectual curiosity, but something deeper. A sense that in confronting the fine-tuning of the constants, they're brushing up against something genuinely profound, maybe the most profound thing a human mind can encounter. Weinberg, who was a committed atheist and had no interest in theological implications, nonetheless described the fine-tuning problem as one that keeps him up at night. He spent decades wrestling with it, not because he expected a neat answer, but because the question itself seemed to point toward something fundamental about the structure of reality. Penrose, who finds the multiverse distasteful and believes in a deeper mathematical explanation, speaks of the fine-tuning with a kind of awe that's palpable even in his densely mathematical writings. And Susskind, who is perhaps the strongest advocate for the multiverse, has said that he came to accept the landscape of string theory not because he liked it, but because the evidence pushed him there, and that sometimes the universe doesn't care about our aesthetic preferences. There's a humility in these responses that I find deeply appealing. These are some of the smartest human beings who have ever lived, and they're all, in their different ways, saying, "This problem is bigger than me. This question goes deeper than I can currently reach." And I'm okay with that, because the reaching itself, the act of pressing against the limits of understanding, is what science is for, and I think that's a good thing to carry with you as you drift off. The universe is not obligated to be comprehensible. It's not required to fit neatly into our theories or satisfy our desire for explanation. The fact that it's as comprehensible as it is, that we can measure the cosmological constant, calculate the energy levels of carbon nuclei, predict the abundances of elements produced in the Big Bang, is itself remarkable. We are 3-pound brains made of carbon and water, and we have figured out that the universe is 13.8 billion years old. that it's expanding at an accelerating rate, and that the constants governing its behavior are set to values of almost impossible precision. That's not nothing. That's extraordinary. And the fact that we don't yet know why the constants are what they are is not a failure. It's a frontier. It's the next chapter in a story that started with Galileo pointing a telescope at the moon, that continued through Newton discovering the laws of motion in a plague-ridden Cambridge, that passed through Einstein reimagining space and time in a patent office in Bern, and that today takes place in underground particle accelerators, in telescope arrays scanning the cosmic microwave background, and in the minds of theorists scribbling equations on whiteboards and napkins all around the world. The fine-tuning problem sits at the convergence of everything we've learned and everything we still need to learn. It draws together particle physics and cosmology, quantum mechanics and general relativity, mathematics and philosophy. It asks us to think carefully about what we mean by explanation, by probability, by necessity. And it invites us, gently, patiently, without rushing, to wonder. That's what I want to leave you with tonight. Not an answer, because there isn't one yet, but the question itself, in all its strange and beautiful depth. Why are the numbers what they are? Why does the universe appear to be calibrated with such exquisite precision? Is it accident, necessity, design, or something we haven't imagined? The question is open, the mystery is real, and it's yours now, yours to carry, yours to wonder about, yours to fall asleep thinking about. The universe made you out of constants that nobody can explain, and it gave you a mind that can notice that fact and be amazed by it. That, all by itself, is one of the most remarkable things that has ever happened anywhere, in any universe, in any configuration of constants. A collection of atoms, bound together by fine-tuned forces, contemplating its own improbability. And this brings me to something I want to spend a little time on, because I think it's underappreciated, and it's deeply relevant to the question of why the constants are what they are. It has to do with the weak nuclear force, the fourth and final fundamental force, the one that doesn't get as much press as gravity or electromagnetism, but that is absolutely critical to the universe's ability to produce life. The weak force is responsible for a type of radioactive decay called beta decay, in which a neutron transforms into a proton, or vice versa, emitting an electron and a neutrino in the process. This might sound like a minor, obscure process, but it's one of the most important reactions in nature. During the first few minutes after the Big Bang, it was the weak force that regulated the balance between protons and neutrons. If the weak force were stronger, neutrons would have converted to protons more rapidly, and the universe would have emerged from the Big Bang with a much higher ratio of hydrogen to helium. If the weak force were weaker, more neutrons would have survived, and the universe would have been richer in helium. Neither of these scenarios is automatically fatal to life, but the downstream consequences cascade. The hydrogen to helium ratio affects how stars form, how they burn, and how long they live. It affects the availability of hydrogen for water, which is rather important for any chemistry even remotely like ours. And it affects the detailed nucleosynthesis inside stars, which determines how much carbon, oxygen, nitrogen, and iron gets produced and scattered into space when stars die. But the weak force plays another crucial role that I find even more extraordinary. It's responsible for the explosions of massive stars, the supernovae that distribute heavy elements across the galaxy. When a massive star exhausts its nuclear fuel and its core collapses, it's the weak force, specifically the interaction of neutrinos with the infalling matter, that drives the shock wave outward and blows the star apart. Without the weak force at roughly its current strength, supernovae might fizzle out. The heavy elements forged in the star's core would remain locked inside, collapsing into a neutron star or black hole, forever unavailable for the construction of planets and life. And here's the fine-tuning. The weak force coupling constant, the number that characterizes the strength of weak interactions, needs to be within a certain range for this mechanism to work. Too weak, and the neutrinos pass right through the infalling matter without depositing enough energy to drive the explosion. Too strong, and the neutrinos interact too readily, getting trapped in the dense core and failing to carry energy outward. The actual value of the weak coupling constant sits right in the sweet spot, where neutrinos are just barely interacting enough to deposit the energy needed for the explosion while still being able to escape the core. So the weak force, like every other constant we've discussed, is finely tuned. And when you step back and look at all four forces together, gravity, electromagnetism, the strong force, and the weak force, the picture is remarkable. Each force, individually, is set to a value in a narrow life-permitting range. And collectively, they work together in a symphony of interlocking dependencies that produces a universe capable of complexity, chemistry, and consciousness. Now, I want to take a slight detour here, because there's an aspect of this story that often gets lost in the discussion of fundamental forces and particle masses, and it has to do with the dimensionality of space itself. We live in a universe with 3 spatial dimensions: length, width, and height, and 1 time dimension. That gives us a total of 4 space-time dimensions. And you might think that the number of spatial dimensions is just a brute fact about reality, not something that needs explaining. But physicists have actually thought quite carefully about what would happen in universes with different numbers of spatial dimensions, and the results are striking. In a universe with 2 spatial dimensions, there would be no gravitational orbits. The mathematics of gravity in 2 dimensions is fundamentally different from 3 dimensions. The gravitational force doesn't fall off with distance in the right way to allow planets to orbit stars in stable, repeating paths. Without stable orbits, no solar systems. Without solar systems, no planets. Without planets, well, you can see where this is going. In a universe with 4 or more spatial dimensions, the situation is even worse. Gravity in higher dimensions falls off too quickly with distance. Orbits are unstable. Even the slightest perturbation would cause a planet to either spiral into its star or fly off into space. Atoms would also be unstable, because the electron orbits around nuclei would be similarly fragile. In 4 spatial dimensions, there would be no stable structures at all. No atoms, no molecules, no solid matter. And time dimensions have their own constraints. Physicists Max Tegmark and others have argued that a universe with more than 1 time dimension would have unpredictable physics. The equations governing the behavior of particles and fields would not have well-defined solutions, meaning that the future wouldn't be determined by the past. Causality would break down. Science itself would be impossible. So even the number of dimensions, 3 of space and 1 of time, appears to be fine-tuned. It's not a continuous parameter, like the strength of gravity or the mass of the electron, but it's a structural feature of the universe that, if it were different, would make complex structures and intelligent life impossible. Let me share one more piece of fine-tuning that I find particularly poignant, and it has to do with the very fabric of space-time, specifically the initial conditions of the Big Bang. The constants of nature tell us about the rules of the game, but the initial conditions tell us about the starting configuration. And it turns out that the starting configuration of our universe was also extraordinarily special. The great mathematical physicist Roger Penrose, who won the Nobel Prize in Physics in 2020 for his work on black holes, calculated that the initial state of the universe, in terms of its entropy, was incredibly ordered. The entropy of the early universe was astonishingly low compared to what it could have been. Penrose estimated the probability of the universe starting in such a low entropy state by chance as roughly 1 in 10 to the 10 to the 123rd power. Let me be clear about what that number means. It's not 10 to the 123rd power. It's 10 to the power of 10 to the 123rd power. The exponent itself has 123 digits. This number is so incomprehensibly, absurdly, overwhelmingly large that there is no meaningful analogy for it. It makes the other fine-tuning numbers, the 1 in 10 to the 120th for the cosmological constant, the few percent windows for the nuclear forces, look like enormous, wide-open targets by comparison. Penrose used this calculation to argue against the multiverse as an explanation for fine-tuning. His reasoning was that even in a multiverse, the probability of randomly producing a universe with such a low entropy starting state is negligible. It would be far more likely for the multiverse to produce a universe that's just barely ordered enough for a single observer to exist. A Boltzmann brain, a fleeting conscious entity that fluctuates into existence in a sea of chaos and fluctuates right back out again. The fact that we observe a vast, highly ordered universe, not just a single brain in a void, suggests that something beyond random chance is at work. Whether or not you find Penrose's argument convincing, it highlights something important about the fine-tuning problem. It's not just about the constants. It's about the whole package. The rules, the initial conditions, the dimensionality of space, the specific mathematical structure of the laws themselves. Every piece seems calibrated. Now, I've been talking for a while about the problem, and I want to spend a few minutes talking about the human dimension of this story, because the fine-tuning debate has brought out some of the most passionate and divisive arguments in modern physics. Careers have been shaped by it. Friendships have been strained. Entire fields of research have been redirected. Take the case of Steven Weinberg and the cosmological constant. In 1987, Weinberg published a remarkable paper in which he used anthropic reasoning, the idea that the constants must be compatible with our existence, to predict the approximate value of the cosmological constant. At the time, the cosmological constant was believed to be exactly zero, but Weinberg argued that if the multiverse existed and the cosmological constant varied from universe to universe, we should expect to find ourselves in a universe where lambda was small, but not zero, just barely small enough to allow galaxies to form. He estimated that the cosmological constant should be about 100 times smaller than the density needed to stop galaxy formation. 11 years later, in 1998, the accelerating expansion of the universe was discovered, and the observed value of the cosmological constant was remarkably close to Weinberg's anthropic prediction. This was a stunning success. Whether or not the multiverse exists, Weinberg's anthropic reasoning had made a prediction that was confirmed by experiment. It was one of the very few cases where anthropic arguments led to a testable, quantitative prediction. Weinberg was a rigorous, careful thinker, one of the greatest theoretical physicists of his generation, the architect of the electroweak unification that earned him the Nobel Prize in 1979. His willingness to take anthropic reasoning seriously gave the idea enormous credibility, but it also made many physicists deeply uncomfortable. The idea that the fundamental constants of nature might not have a unique, necessary explanation, that they might simply be environmental accidents, varying from universe to universe, felt like giving up on one of physics's deepest goals, explaining everything from first principles. This tension is still alive today. When you go to a physics conference and bring up fine-tuning, the room divides. There are the multiversists, who argue that the landscape of string theory and eternal inflation make the multiverse essentially unavoidable, and that anthropic selection is the best explanation we have for the constants. There are the skeptics, who argue that the multiverse is untestable, and that physics should keep searching for a unique theory that determines the constants. There are the agnostics, who find the question fascinating, but think we don't yet have enough information to choose between the alternatives. And there are a few iconoclasts who argue that the fine-tuning problem is overstated, that the life-permitting range of constants may be wider than we think, or that our understanding of what life requires is too narrow. One of my favorite voices in this debate belongs to the physicist Lee Smolin, who proposed an idea so creative and so strange that it deserves its own moment. Smolin suggested a theory called cosmological natural selection. The idea is this: when a black hole forms, it might give birth to a new universe on the other side, a baby universe with slightly different values of the fundamental constants. Those new universes that happen to produce many black holes would, in turn, produce many offspring universes, which would inherit their parents' tendency to make black holes, with slight variations. Over many generations of universe reproduction, this process would select for universes that are maximally efficient at producing black holes. And here's the punchline: universes that are good at producing black holes also happen to be universes with long-lived stars, complex chemistry, and conditions favorable for life. It's a kind of cosmic Darwinism. The universe isn't fine-tuned for life directly, but for black hole production, and life comes along as a side effect. Smolin's theory has been criticized on various grounds. Some of its specific predictions have been challenged, and the mechanism by which black holes produce baby universes is highly speculative. But what I love about it is the sheer audacity of the imagination. It takes the fine-tuning problem and reframes it entirely, replacing design and coincidence with a natural process of variation and selection. It's physics doing what physics does best, taking a mystery and proposing a mechanism. Let me tell you one more story before I start to bring this all together, because it captures something essential about the spirit of this quest. In 2006, a group of nuclear physicists, led by Evgeny Eppelbaum, published a paper exploring what would happen if you changed the masses of the up quark and the down quark, the two lightest quarks, the building blocks of protons and neutrons. They used sophisticated numerical simulations to map out the parameter space, asking, for what combinations of quark masses do you get stable nuclei, stable chemistry, the possibility of complex structures? And what they found was a narrow, irregularly shaped region in the quark mass parameter space, a small island of habitability in a vast ocean of sterility. Move outside that island, and protons or neutrons become unstable, or nuclear binding energies change so drastically that complex atoms can't form. Our universe sits on that island, not at the center, not at a particularly special point, but squarely within the habitable region. If the quark masses were much different, we'd be in the ocean. Other researchers have since extended this kind of analysis to other parameters. Dean Lee and colleagues mapped the parameter space of the strong force in the region relevant to carbon and oxygen production. Alejandro Jenkins explored the fine-tuning of the Higgs field, whose vacuum expectation value determines the masses of all the fundamental particles. Luke Barnes, a philosopher of physics who has done perhaps the most comprehensive survey of the fine-tuning literature, has cataloged dozens of independently fine-tuned parameters and shown that even accounting for correlations and compensating adjustments, the life-permitting region of parameter space is genuinely small. The picture that emerges from all of this work is consistent and striking. The universe we live in sits in a tiny, special region of a vast space of possibilities. The constants of nature, the initial conditions of the Big Bang, the dimensionality of space, the mathematical structure of the laws, all of it seems calibrated, and nobody knows why. So here we are, lying in the dark, thinking about the most basic question you can ask about reality. Why is the universe the way it is? Why do these numbers have the values they have? Is it luck? Design? The multiverse? A deeper theory? Cosmic natural selection? Something we haven't thought of yet? I don't have the answer. Nobody does. And I think there's something genuinely beautiful about that. We are a species that evolved on a small, rocky planet, orbiting an average star in an ordinary galaxy. And we have figured out, through centuries of careful observation, mathematical reasoning, and sheer stubborn curiosity, that the universe appears to be balanced on a knife's edge. That the numbers written into the laws of nature are suspiciously, almost impossibly, just right. And we've gotten far enough to frame the question precisely, to map the territory of what we don't know, but not yet far enough to answer it. Think about where you are right now. You're lying somewhere comfortable, probably in the dark or near dark, and the atoms in your body, the carbon in your muscles, the iron in your blood, the calcium in your bones, were forged in the cores of stars that lived and died billions of years ago. Those stars could only exist because gravity was the right strength. The carbon could only be made because of a specific energy resonance that Fred Hoyle predicted in a Cambridge office in the 1950s. The atoms in your body hold together because the strong force is just strong enough, and the electromagnetic force is just the right intensity, and the neutron is just barely heavier than the proton. The space around you has 3 dimensions because, apparently, 3 is the only number that allows stable orbits and stable atoms. The universe itself is expanding at a rate governed by a cosmological constant that is 120 orders of magnitude smaller than what our best theories naively predict. And yet, that absurdly tiny value is exactly what's needed for galaxies to form and for someone like you to exist, right now, in this moment, thinking these thoughts. Every breath you take is an act of staggering cosmic improbability. The oxygen you're inhaling was made in a massive star that exploded, scattering its contents across light years of space. That debris eventually clumped together to form a new solar system, our solar system, about 4.5 billion years ago. The oxygen found its way into molecules, into an atmosphere, into your lungs. And the entire chain of events that brought it there depended on numbers that could have been different, on constants that could have had other values, on initial conditions that could have been arranged in any of an astronomically large number of other ways, almost all of which would have produced a dead, empty, sterile universe. But they didn't. The numbers came out right. The universe opened its eyes. Stars burned. Elements formed. Chemistry got complicated. On at least one small planet, molecules learned to copy themselves, and those self-copying molecules became, over billions of years, unimaginably more complex, until eventually, they became something that could lie in the dark and wonder why any of this exists at all. I don't know if that's luck, or design, or the multiverse, or some deeper law we haven't found. But I know it fills me with a quiet, steady sense of wonder. Not the loud, dramatic kind, the bedtime kind. The kind you feel when you look up at the stars and realize that you're looking back in time, that the light hitting your eyes has been traveling for years, or centuries, or millennia, and that the atoms in the stars that emitted that light are governed by the same fine-tuned constants as the atoms in your own body. You and the stars are made of the same stuff, playing by the same impossibly precise rules, and neither you nor the stars know why those rules are what they are, And you know what? For tonight, I think that's okay. Not knowing is not a failure. It's where the story is right now. Physics has been asking harder and harder questions for 4 centuries, and it keeps finding deeper and deeper answers. Newton explained why apples fall. Einstein explained why Newton's equations work. Quantum mechanics explained why atoms are stable. And maybe, someday, someone will find the theory that explains why the constants have the values they do. Maybe it will be a young physicist who hasn't been born yet, someone who will look at the problem from an angle no one has considered and find a connection no one suspected. Or maybe the answer is already lurking in the mathematics of a theory we have but haven't fully explored. Or maybe, just maybe, the question itself will turn out to be the wrong question, and the right question will be something we can't even formulate yet. The fine-tuning of the universe's constants is one of those rare problems that sits at the intersection of physics, philosophy, and something that's almost spiritual. It asks us to confront the possibility that the universe is not just improbable, but seemingly orchestrated, that the conditions for our existence are not generic but deeply special. And whatever the ultimate answer turns out to be, the question itself is a monument to the human mind's ability to look at the cosmos and see, beneath the surface chaos, an exquisite and unexplained order. So, rest with that tonight. Rest with the knowledge that the universe didn't have to work, that the numbers didn't have to come out right, that every atom in your body, every photon of light from the lamp you just turned off, every gentle pull of gravity keeping you on this bed, all of it depends on a set of constants that are tuned to an almost impossible precision, and nobody knows why. Not yet. But we're asking. We've always been asking. And the asking itself is one of the most beautiful things our species has ever done. Close your eyes, if they're not already closed. Feel the weight of yourself against the mattress. That's gravity. Just strong enough to hold you here. Just weak enough to let the stars burn for billions of years. Feel the warmth of the blanket. That's electromagnetic interactions between the molecules in the fabric and the molecules in your skin, governed by a fine structure constant of 1/137. Listen to the silence around you. That silence is full of neutrinos, trillions of them, passing through your body every second without interacting, ghosts of the weak force, the same force that makes supernovae explode and scatter the elements of life across the galaxy. You are made of the universe's finest work. You are the constants of nature, arranged just so, against all odds, into something that can wonder about itself. And that's enough. That's more than enough. That's everything. Let yourself drift now. The universe has been asking these questions for 13.8 billion years. It can wait a little longer for the answers. And when you wake up tomorrow, the constants will still be there. Gravity still pulling. Light still traveling at exactly 299,792,458 meters per second. The strong force still holding every atom in your body together with that precise, improbable, perfect strength. The numbers are what they are. Nobody knows why. And the not knowing is itself a kind of wonder. Good night.